started a bunch of cool pieces together. I thought it was fun doing that. Wrote a book about that experience. He's come here again, which is great for us. He's, in a sense, working as a development person for us, helping us raise money for different projects, and just taking a real interest in art, AI in particular, and also teaching, continuing the course of STEM here. So with that, here I am.
I'm going to stand over here. I'm old and I forget what I'm going to say. Telecom. Okay, artificial intelligence. First 100 years. I've got a lot of stuff to cover in half an hour. Put on your 3D glasses, get your popcorn. So I'm going to talk today a little bit about the intellectual foundations and the future direction of AI. And I'm going to try to propose an answer to that very difficult question: what is artificial intelligence? Is it a quest to reveal a fundamental truth about intelligent life? Or is it just a scavenger hunt to find novel applications of computers? I'm going to try to compare the two dominant approaches to AI, which is called the symbolic inference approach, the logical approach, and the machine learning approach, which many of you are familiar with. And I'm going to try to explain how the dramatic increase in computer power is going to shift in an emphasis from the former of those to the latter. And from that, I'm going to suggest what I think makes artificial intelligence a unique and coherent engineering discipline. And then I'm going to turn to the future, the next 50 years. Talk about the societal changes that we're likely to face as a result of the work that you guys are doing in robotics today. And I'm going to argue to you, you bear considerable responsibility, the impact that your work is going to have on society. I want to talk about what it is. So let's start with the history. See these little wooden wiggle snakes? Familiar with those children's toys? So why should we care about history? Because the knowledge of how we got to where we are really helps us to better understand or to better decide where we're going. Now, it may feel to you today like you have complete freedom to work on whatever you want, but you don't. The truth is, your current research is largely driven by what you believe may be possible. What you believe may be possible today is based on what other researchers accomplished yesterday. So like the pieces of a wooden snake, you have some degrees of freedom, but your options are probably more constrained by the previous piece than you may realize. So today I'm going to try to show you some more parts of your own snake you may not have seen before. And seeing that arc can help tell you what direction your snake is going and help you understand how to move this snake along its path to the next generation. So let me talk a little bit about the AI lab. I know some of you are from different labs, but from my point of view, you're doing robotics, you're doing arguably what AI is. So the AI lab at Stanford, interestingly enough, can be traced back much further than you might think. Really to the founding of the electrical engineering department here at Stanford in 1892. And you might ask, 1892? What could EE mean in 1892? The answer was power electrics. This is delivering power via electricity to our lights and motors and things like that. Now, in 1892, the existence of electricity had been known only for about 200 years. And it was regarded mainly as a natural environmental phenomenon, sort of like lightning, and not something that could be harnessed or used to do work. And in 1892, it was only 10 years earlier, in 1882, that Edison, Thomas Edison, turned on the first electric grid in New York and provided electricity to 59 customers in lower Manhattan. So what exactly were your predecessors, Stanford EE students, studying back then? The course notes that I've run across in Stanford archives cover alternators, synchronous motors, transformers, transmission lines, and other topics like that. But by the mid-1920s, the character of the department began to shift from power generation and power distribution to what they called at the time electrotechnics. And that's what we now know as electronics. There's a guy named Fred Terman, you may have heard the name, joined the university, and he was very interested in how electricity and radio waves could be used for communication, or what we now think of course, as processing and transmission of information. Now, basically, if you think about it, Terman was exploring a very simple question, which is what else can we do with electricity? Now, by the early 1940s, this question, what could you do with electricity, proved to be critical to this nation's survival in the outbreak of World War II. There was a new class of electrotechnical devices, which were at the time called electronic calculators. These are the stored program electronic calculators, which were the predecessors to, or the first computers. They were put into service along with every able-bodied person. Now, what for? The military needed to develop what were called ballistics firing tables. These were an enormous list of calculations in order to help the soldiers during World War II set their guns, aim their guns to be able to hit their targets accurately. And now originally, these tables were computed by hand. Now it took up to 20 hours of painstaking work by a human calculator, and they were called calculators. That was the name of a profession, to produce one single ballistics trajectory. But with one of the electronic calculators, that 20 minutes could be reduced to about 15 minutes. So after World War II, and all this tremendous investment that took place in electronic computers, people were facing the challenge of finding peacetime uses for all this wonderful technology. They didn't need any more ballistic systems. So the question came up yet again, what else could you do with electricity? What could you do with these devices? And by the 1950s, an answer emerged, and that was data processing. Many companies, the most prominent of which you know is IBM, saw a market for data processing tools as productivity aids. They could replace legions of clerks that were powering the corporate and government offices at the time. So now we're up to the part of the story you're probably familiar with. The question came up again. If computers could crunch numbers, and if computers could process data, why couldn't they think? After all, as the reasoning went back then, it's a simple matter of logic. That's what people thought it was all about. So, in the summer of 1956, a group of scientists got together for an extended working session at Dartmouth in the summer. And John McCarthy, who was then at Dartmouth, he hosted the conference along with Martin Minsky, Claude Shannon, and Nathaniel Rochester. All those guys have very interesting stories. But to understand the original intention of these guys, who were the founding fathers of artificial intelligence, it's actually worth reading the actual text of their summer proposal that they put in. And that was that this study is to proceed on the basis of the conjecture that every aspect of work or any other feature of intelligence can in principle be so precisely described the machine can be made to simulate. They went on to say an attempt will be made to find out how to make machines use language, form abstractions and concepts, solve kinds of problems that are now reserved for humans, and have these machines improve themselves. Now, that was a very modest research proposal that they were going to accomplish all of this during the summer of 1956. As you hopefully know, John McCarthy, who wrote those words, founded the Stanford Artificial Intelligence Lab in 1965, and he was director here until 1980. He literally named the field of artificial intelligence when he drafted that proposal for the first use of the term artificial intelligence. Now, by the way, to give you a sense of continuity in history, Professor McCarthy's last office was 208, right upstairs. He was there until, I think, 2 years ago? About 2 years ago. Okay, so let me pause here at the dawn of the age of AI and sum up a little bit. Returning to my snake analogy, what's the common theme here? Where exactly is the snake living? Our work today in artificial intelligence traces its intellectual ancestry in an unbroken chain all the way back to the late 19th century. The common thread is that at each step of the way, from electric motors, circuits, electronic calculators, data processors, artificial intelligence, engineers have worked to find ever more useful applications for electricity. So it's the spirit. What can we do with electricity? In my view, is animating the work that's going on in the lab today. It's still evident in the work we do in robotics. Now, you might argue, well, that's not really true. After all, in theory, computation is independent of the means by which it's implemented. Computers could have been made out of mechanical parts, like this Babbage's difference engine, or from biochemical components, the way animals are made. And that the same rules of computation would have applied. But it's more than a mere accident that modern computer science arose in the context of electronic circuits. If we were building our computers today with mechanical or biochemical computers, I think the different issues of theory and different problems would be relevant and therefore be pursued. So, for example, it would be unlikely we'd be studying networking theory if our computers are mechanical, because it's hard to imagine how these mechanical devices can transmit information over long distances. It's also unlikely we'd be studying computational complexity theory if the computers are biochemical, because the purpose of complexity theory is really to help us understand and to tame the very limited serial nature of the ongoing architecture. So here's today's lesson. Okay, students, write this one down. Today's lesson is this, that the problems that we work on and the tools that we develop are really driven by our chosen technologies. Today's robotic systems are a natural extension of what Fred Terman called electrotechnics. Intelligent robots are really, in my view, just very sophisticated electromechanical machines. So, to sum up on this, here we are, over a century after the founding of electrical engineering here at Stanford. A century later, and we're still exploring the potential uses of electricity for teaching electrons new things. Okay, so let me pick up the story again at the dawn of the age of AI. Now, the participants of the Dartmouth conference, there's some, by the way, they actually look like that. I met them, they're all fuzzy and out of focus. A lot of them had their own view of how to best approach AI. But John McCarthy in particular believed that logical inference was the key to, as he put it, simulating intelligence. It's very interesting that he thought intelligence needed to be simulated and that it was not something that could be duplicated. That's a different lecture. Now, if you walk around these halls today, you're really going to find a minority of people who are pursuing McCarthy's vision of artificial intelligence as being based on logic and inference. Instead, the department is much more focused on a different approach to AI, which is basically machine learning, where you're inducing things from large data sets with sensory input. Very relevant to what goes on in robotics. Now, to understand what happened, we first have to understand what's different and what's the same about these two approaches. So to find that out, let's start to take a closer look at the symbolic systems and machine learning schools of artificial intelligence. Now, the first thing you notice is that they focus on different problems. The symbolic systems school, that's the left one here, sees inference and reasoning as the hallmarks of human intelligence. And so they view that as the most promising approach to achieving artificial intelligence. That's why that field is focused on things like heuristic search, computational logic, the explicit representation of expert knowledge of rule-based systems, something I was involved in when I was here in 1980. And by contrast, the machine learning school regards perception and real-time engagement as the measure of success. Obviously more relevant to robotics. That's why we focus on tests in robotics and other areas of AI, like speech recognition, vision, autonomous driving, or those great pressing societal issues like blocking spam or preventing credit card fraud. So that's a little abstract, but let me see if I can describe the difference between these two schools of thought in a little bit more colorful way, and hopefully instructive. Imagine we're in Scotland Yard, and we find ourselves challenged by a dastardly villain who's terrorizing London. Now, who should Scotland Yard turn to? Of course, there's Sherlock Holmes. He believes in reasoning. He tackles this problem by sitting in an armchair, lighting a pipe, and using his powers of deduction to entrap his adversary by outwitting him at his own game. On the other side, we have Spider-Man. Spider-Man believes in perception. He gracefully swings his way around London until his spider sense starts to tingle, and then he engages his adversary in physical combat. Now, these represent the two different approaches to AI. Try to imagine these two having a conversation with each other, trying to debate whose approach is better. I doubt that either one would get very far with the other. So, the plain truth is that you cannot program a robot to ride a bicycle by interviewing Lance Armstrong. On the other hand, you can't prove Fermat's last theorem by examining enormous numbers of data sets of inches. So this is a little bit about the differences in the approaches, but what do they have in common? That's where things get interesting. Now, there isn't necessarily a crisp or a right answer to this, but I do want to give you a couple of thoughts. In my view, a hallmark of an AI system is flexibility in the face of novelty. An AI system has to do reasonable things when it's confronted with new or unexpected input. Now, that novel input might be a flightless bird, a strange question in English, if that's English, and some kind of novel, brilliant new opening move in chess. So the frequent characteristic that I see in artificial intelligence systems is either they find generalizations or they use generalizations to deal appropriately with unanticipated inputs. The important thing about an AI system is how gracefully it fails. That's important how they succeed. How the program addresses a problem, therefore, is as important as what it does. Now, this is particularly true of robotic applications. As you know, a wrong move can kill someone, or it can break the device. And whether you're capturing human knowledge in an expert system, or you're digesting a large number of examples in machine learning, AI systems typically represent generalizations about their domain that permit useful predictions in novel circumstances. Now, these generalizations, presumably what they do is they capture something fundamental about the structure of the real world. So, in short, I think that most of AI research can be characterized as a search for useful generalizations. I don't have time to cover this in more detail, but I think there are actually mathematical definitions of what that means and how it can be applied and how it can drive future research. In the real world, we call these things lessons learned. That we can apply in the future. So, this is just a suggestion. Perhaps we could describe artificial intelligence as the engineering practice of algorithmic generalization. But I still haven't explained why the symbolic system school of thought was dominant 30 years ago when I was here, and why machine learning is dominant now. And the simple answer is the available technology to move rapidly. This is computers, storage, networks, data change. Now, it's difficult for me to communicate how much they've changed. They haven't changed just a little bit. They haven't changed just a lot. They've changed a I'll use a technical term, a ridiculously humongous amount. And that changed what was possible. You're probably familiar with Moore's law, that computing power tends to double every 18 months or so. Well, over 30 years, that's 20 doubles. If you guys could do the math, what is 2 to 20? Okay, I'll do that. That's literally a factor of 1 million. Now, to try to bring this to life for you, I try to think, well, how can I come up with some kind of intuitive analogy for what a factor of a million is? Well, here's one. It is literally twice the difference in the speed between the speed of the snail and the speed of the space shuttle in orbit. That's only a factor of 500,000. Now, my MacBook sitting right here literally has hundreds of times more computing power than was available to the entire computer science department when I was here 30 years ago. Imagine everybody in the room trying to get their email and do all their research, sharing one little Mac laptop. There's something that's 1/100th of that. The Apple II, I actually worked on one of these. Interesting story, but just got time for fun stuff. Important work to do. The Apple II that I worked on as a graduate student here, it could hold up to 48K of RAM. That was as much as you could get into the box. That's not quite enough RAM to hold 1 second of CD quality music. Now compare that to the 12 days of music that I can hold on my iPhone. That's a factor of 1 million. At some point, my point is that at some point, a large enough quantitative difference like that becomes a qualitative difference. And this is just wild and clearly beyond that point. So for all practical purposes, today, we are using very different technology than we were 30 years ago. And that's why the problems that we're working on and the things that we're doing are very different than they used to be. So how has this affected our selection of tools and approaches? And the advantage of the simple systems approach is pretty simple. You can do a lot with a little. You can input a few simple facts as input. It could reason its way to some kind of valuable conclusion, such as a mathematical theorem or a chess victory. And simple systems approach didn't require a whole lot of data because there just wasn't a whole lot of data and you couldn't fit a whole lot. So the field was naturally focused on very well-defined limited domains, like chess playing or like language parsing. And that was a good match for what was available for technology 20 to 30 years ago. Now, by contrast, machine learning can find weak signals in very noisy info, as long as it has access to enough data. It can deal with messy, real-world domains, and can reach tentative or provisional conclusions. Most important, the results to date that I've read suggest that it tends not to hit asymptotic limits very quickly. So as long as there is more data available, these systems become better and better at what they're trying to do. So the machine learning approach is a much better match to today's highly networked and data-intensive world. So now, we're going to repeat today's lesson. This will be on the final. The problems that we work on and the tools that we develop are driven by the available technology. It's no wonder that we're using different tools today on different problems. This symbolic systems approach is appropriate for technology today. The machine learning is appropriate for today's technology. And now things get weird. What does this all mean to you? Average Stanford grads. Joe Sixpack of computer science. The point is, you're here at one particular point in time, and you haven't necessarily seen this whole arc of history, but it's continuing. And the scary thing is, if it continues at the same rate, and there's every reason to believe it will, within the next 15 years, computers are going to have the processing power and storage capacity of a computer that has the processing power and the storage capacity of the human brain is going to cost $1. So we need to be thinking today about what that's going to mean, the kinds of systems, the kind of problems we're going to need to start to solve. So what's going to happen in the next few decades? One likely development is we're going to start building robots that are both physically and cognitively autonomous, make their own decisions and engage in the environment without human guidance. And these machines are going to collide head-on with issues that have plagued philosophers and theologians for thousands of years. And what are these questions? The first is, are we something more than our own physical selves? Are we vessels for some kind of supernatural, non-physical, animated spirit? Or are we just sophisticated machines that are made out of meat? Descartes worried about this in his concept of mind and body dualism, where he just said, look, these things are different. You got the physical world, and you have sort of this mental world, and they're different. And his concept became the basis for a very uneasy truce between religion, which dealt with the mental domain, and science, which dealt with the physical domain. So we're kind of living in that Cartesian view of the world while we work on physical stuff. And this whole thing about mind and that's something different. But they're about to collide, and they're going to collide in the next 15 years. The second question is, are we unique? In particular, can only people, and perhaps few animals, have what you might call a mind? Or is there a way to build something that deserves the same special status that we accord to humans? It deserves our empathy. It deserves our moral standing. Now, it seems plausible to me that we have an instinct that's developed over our evolutionary past for recognizing things that are, quote, like us. And these are things to which we attribute subjective experience and feelings, and therefore we give them moral standing. And these, of course, today are mostly other people. Our subjective experience and our belief that other people have that same subjective experience may just simply be the necessary foundation for this instinct. Now, why is this useful? The evolutionary value of this instinct is obvious. It helped us perpetuate our species because we help each other because we think that other people have similar to us. As social animals, we're willing to help each other, even sometimes to the point of sacrificing ourselves, because we believe that others are experiencing the world the same way that we do. The problem is, time is coming during your lifetime when this instinct is going to lead us astray. Our intuitions are not going to suit us at all to live in an age of intelligent machines. Now, intelligent robots may rival human intelligence. They may even express beliefs and exhibit intentions and feelings. But in my opinion, we shouldn't be fooled into extending our circle of kinship to include them. Now, this is going to be really challenging. When a robot comes into your office weeping because it broke a wheel, or it's begging you not to turn off the light at night because it's afraid of the dark. But I will argue to you, we should not grant them human moral standing or the courtesy of our empathy. That's not what the instinct that we have was intended to be. Now, in the next few decades,